Sir, in the lecture number 8,
8.
8,
Okay, just a second.
a time strap of 25.12, 25.
Lecture number 8. So it will be,
Mm.
it's week 3, right? No, week 2.
Week 2.
Last
Week
one.
2. Yes, sir.
Just say the slide number.
Slide number will be around last will be X. There is a X
Oh, you can't see
logo
my screen, right?
and will be
Just a
there.
second. Let me share my screen. Hmm. Hmm. Okay. So now you can see my screen, right?
Yes, sir.
Okay. So which slide?
So, is this a 8 lecture number 8?
Let me check.
This is 10, sir. I think.
Oh
It is
yeah,
PDF.
it's
It is
10.
showing 10.
Hmm. So this one should be 8. Hmm. Go ahead.
Uh, at last,
Hmm.
it is in that just move upward,
Upward. Okay.
just upward.
Hmm.
In this one, the excess is some terms will be there as a slow variable and a fast variable like that.
Just
So
a
slow
second.
variable control.
Excess is compared with its reference excess star. The error is regulated by the slow variable regulator RS. Okay. Okay, here. Yeah, this regulator has a dynamic performance such as D is directly adjusted so that the slow variable remains regulated.
Just move upwards also.
Huh.
This in this one fast variable, the capacitor voltage is slow and gate current is fast like this. It is given.
But we are only sensing the capacitor voltage, right?
Yes, here it is
So
a
this is
slow one.
voltage control.
Voltage control only.
Hmm.
That is what I am asking yesterday.
Hmm.
Regarding the why the voltage control or some points will be given are given in the upward slide, right? Just more.
Okay, okay, I'm just checking.
And that, oh, don't move that much, sir.
Okay, okay,
It
okay.
is just in that above slide only.
Achha, let me check. These are
This one only.
control problems and the application control.
The for rectifier capacitor voltage is slow and gate current is fast. Uh, and motor
For
drive.
rectifier,
Uh,
capacitor voltage is slow and grid current is fast.
Control strategy applied to this often deal with the regulation of the variables with the different dynamics.
Okay, acha, I got it. So this portion is your doubt, right? That why these
Yes, sir.
points and why
It's,
this is made slow, means there are
yes,
different.
yes.
Okay, so let me discuss these 3 points separately. So
Okay.
let's take the easier one. So motor drive. In motor drive, motor speed is slow, current is fast. This is
Yes, sir.
obvious because speed is a mechanical
It's,
quantity
yes, sir.
and its dynamic is way slower. So
Yes, sir.
hence it is in the slower control. The control loop of speed is slow, and the since current being a it's a
Electrical
electrical quantity.
parameter.
It has a higher faster time constant, so that's why it is fast. So it's very much clear. So let's go to the next one, that is the for rectifier. So for rectifier, uh, so number one, so we have rectifier scheme. Rectifier is basically the inverse of the inverter stage, right? So
Yes, sir.
this is not, this is a uh, what should I say, uh, by rectifier I don't mean passive rectifier which is diode bridge rectifier. This is a
Mm.
active rectifier stage. So how it happens is, you have three, just the opposite of the, oh sorry, inverter stage. So okay, so then we have the capacitor, the DC link capacitor, or means the DC capacitor, not link, and we have, let's say, the load R, right?
Okay.
See, these are all L, and we this is suppose connected to some three-phase AC system. Okay, so here what is done is, this current, this voltage is the output voltage.
Yes, sir.
So what we essentially control is this output voltage
Output voltage.
in case of rectifier. So this is rectifier stage we are discussing. So in rectifier, our primary objective is to control output voltage. So to control the output voltage, so that whatever is our primary objective will be in the slower loop. But
Based on the sensitivity we select, or the based on the what we need to control, that one is a slow control.
hmm? Come again.
Is this based on the sensitivity, how much, how fast it is changing, we are
Yes.
doing, or
No, see, sensitivity is when you have different phenomenon, like when you have a mechanical phenomenon and the electrical phenomenon, you know that the sensitivity of electrical is way high because its time
yes,
constant is very small compared to mechanical. So there you can say, but when you have both electrical quantities, how can you differentiate the time constant between the two?
okay,
So you cannot have a sensitivity analysis in when both of them are electrical, or both of them are same
domain
domain.
one.
So that's why I said that motor is very easy, because it has two different domains. So since it has two different domains, their time constant only makes the control control different. Like speed will be a slower loop in the outer loop, slower, and the current control will be the faster. And also this way also we can say the primary objective is, for a motor, is speed control only, right?
Okay.
in motor, what do we control?
Motor speed only we need to control.
Torque we cannot measure, right?
Yes.
How do we cannot measure torque because torque is not
Yes, yes,
a
yes,
measurable
yes,
quantity. So only thing that we can measure in the is the speed. So
yes.
that way also we can say that the whatever we need to control is the speed. So our primary objective is to control the speed. So that's why we go for we make speed slower the dynamic. Also this mechanical, it is mechanical, so it will eventually be slow. So it will be in the outer loop and motor current loop will be in the inner loop. But in case of rectifier or inverter, both of them are either current and the other will be voltage and vice versa. So how do you differentiate between current and a voltage, which one will be slower or faster? So there what is the thing is that the primary objective is what, in case of rectifier it's the capacitor voltage that
Voltage.
we have to control, right? So
Yes.
actually it's the same device, the control just changes. I will show you. In rectifier what happens, so this is the IL, right, and this is the output voltage. So here the primary objective is to control the output voltage. And how do we after controlling the output voltage, what we also want to achieve along with that is uh, unity power factor,
Yes, sir.
right?
Yes.
That can be achieved by controlling the IL current as well.
Mm.
So the primary objective is to control the output voltage, so it is in the outer loop, and the control of the current is secondary, so it is in the inner loop. So capacitor voltage, it will be slow since it is in the outer loop, and grid current will be fast. Now how to make that, I have already in the last session I told you, I guess, that to make the uh, response of the inner loop faster, what you have to ensure is that the loop gain not the loop gain, the loop transfer function of the inner loop should have a gain crossover
Time comes.
frequency. Yeah, you can say it that way also. So it should have a gain crossover frequency which is 10 times that of the outer loop, which essentially results in a settling time. Just a second. Huh. A settling time of the inner loop to be faster than that of the outer loop. So why 10 times? Because uh, in Bode plot what we see is that we essentially check for every decade frequency, right? So 10,
Yes, sir.
then 100. So if you can ensure that it's 10 times, so it's a pretty much you can like when you consider the outer loop, you can consider the inner loop to be if you have the gain to be 1 unity gain, like the
Mm.
dynamics can be assumed to be equals to the gain. There is no dynamics, the DC gain of the transfer function, right? If the inner loop is faster, what we can essentially say is that the inner loop can be replaced with its DC gain when we are analyzing the outer
Uh,
loop.
I'm not able to get it, sir.
Okay,
Just
okay. So just a second.
give it an example or just
Okay,
write it.
okay, no issue, no issue. So let's take an example, this rectifier example only. uh, we
Just
have
draw a block diagram of that, just a
that
box
only
one
I'm
only.
drawing. uh,
Okay.
so the inner loop is current loop, right?
Yes, sir. Yes, sir.
Okay, so IDEF, and here is my sensed I or IL. okay, whatever you can consider IL. So this is the, this goes to a, this is controller, it, the inner controller, then comes the, so in case of this kind of control where two variables are inferred or there is a nested control loop, we have to divide the whole plant into two portions. Okay.
Okay. Plant means this one only, no, right, sir? Rectifier.
So plant, let's say plant 1, then we have this will give me the IL, which is which is being sensed here, and next, okay, this is the current, and then we have the other portion which is plant 2. So these are basically the transfer functions. These are, you have to derive from the dynamics of the system. So if this is IL, so
System model.
this plant 2 portion will give you the output voltage also. Output voltage. This output voltage again can be sensed. And again compared. Okay, this is plus, this is minus. Again here it will be minus, and we will consider a VO reference, and again we have a
Controller.
outer controller. Let's name them. This is H1, this is G1, this is G2, this is H2. G1 and G2 are obtained from the dynamics of the plant. H1 and H2 you need to design, right? Now H1 and this is need to design. So what is the loop transfer function for the inner loop? G1 into H1.
G1 into H1.
What is,
Minus.
right? And now is the thing. So what you need to ensure, and let us consider that this loop gain has a unity DC gain,
Okay.
right? It can be different also, there is no issue with that. Means it can be some k, some constant. I'm just considering to make you understand that it's unity, it has a unity DC gain. Okay.
Okay.
So then what we can write the outer loop gain is, so it's the inner loop gain. Okay, the power is out actually, so let's see. And the outer loop gain can be considered to be G2 into H2 if it is unity, right?
And these will also will come, right? G1 and H1 also.
G1 and
All loop.
H1 won't come. That's what I'm saying. To ensure that G1 H1 doesn't come, you take consider the Bode
That
plot of this.
make as a 1.
Yeah, that will reduce to 1. I'm considering that its DC gain is 1. So if you consider the Bode plot of this and Bode plot of this, if you can ensure that the crossover gain crossover frequency of G2H2 is a decade less, at least a decade less compared to that of G1H1, you can easily say that the inner loop gain is this, the outer loop gain is this. You can design the controllers H1 and H2 separately. Now,
Sir, but outer loop gain will be the total of it is coming inside. Then we don't calculate the H2 and H1, G1 and G2.
come again.
The outer loop gain, I am having doubts, sir. Why it is G2 into H2 only?
Because G1 into H1, I'm saying that we, yeah, okay. Let me show you using Bode plot only. So, okay. So let's say we have a unit gain. So this is 0 dB line. So
Hmm.
one is like this. The other one. Let's choose another color. Is like this, right? So this is G1 H1. Now, whenever you are considering this the outer loop is the slower loop, right? So
Yes.
its crossover will be at least one decade early. Means then only you can ensure that the settling time, since omega uh, g1 no, omega g2, this is omega g2 and this is omega g1, let's say. So ts1 will be much greater than ts2, to ensure that the omega g1 should be greater than 10 times omega g2. And if you can ensure that, as you can see throughout the duration, it's dynamic. So here it is attenuating, right? It's Bode magnitude characteristics is attenuating.
Yes, sir.
So throughout the duration before it's attenuating, it is experiencing a unity gain 0 dB from the inner loop, right?
Yes.
So that's what I'm saying. So hence it is, if we consider it to be unity gain, then we can say it to be G2H2.
Hmm. I am asking that if